The next topic is multi-rate data signal processing. The processing of a discrete time signal at different sampling rates in different parts of a system is normally termed as multi-rate data signal processing. The discrete time systems which employ the sampling rate conversion while processing a discrete time signal is called the multi-rate DSP system. The process of converting a signal from one sampling rate to another sampling rate is the sampling rate conversion. Mainly, the sampling rate conversion operation can classified into downsampling and upsampling. Downsampling is the process of reducing the sampling rate by an integer factor, whereas the upsampling is the process of increasing the sampling rate by an integer factor. Coming to the detail of downsampling, as I said earlier, downsampling is the process of converting the sampling rate to a decreased size. That means the processing of reducing the samples of a discrete time signal is termed as downsampling. Let x of n be the input to a downsampler, which downsamples by a factor m. Then y of n can be represented. Y of n is the output, which can be represented as x of mn. The device that performs downsampling is called a downsampler. The symbolic representation of a downsampler is represented by this figure. X of n is the input to the downsampler and y of n is the output to the downsampler. And the system downsampler is represented by an arrow, down arrow, followed by the letter capital F, which means that the system is a downsampler by a factor of m. Let us consider an example. X of n is equal to 2, 1, 3, 5, 7, 2, 1, minus 3, minus 2, minus 1, 0, 5, and 3. I am taking a downsampler. I want to take y of n as x of 2n. So the y of n can be represented as 2. This 2 will come here. Next is 3. This 3 is the value. Next is 7, 1, minus 2, 0, and 3. This is x of 2n. So symbolic representation is downsampled by 2, x of n, and this is y of n. If I want to take y of n as x of 3n, then y of n can be represented as 2 Next is 5, 1, -1, and 3. So from this calculation of x of 2n, the y of 2n is retained every even indexed sample, that is x of 0, x of 2, x of x of 4, x of 6, like that. Every even indexed um, sample is retained and discarding all other samples. In y of 3n, sorry, x of 3n, that is y of n is equal to x of 3n, the downsampler by a factor of 3 implies that it retains every third sample and discards the other. So mainly a downsample by a factor of m represents it will retain every mth sample and discards the other sample. Okay, so next portion is spectrum of downsampler. Spectrum of a downsampler. Let us take x of n as the input of the downsampler, m be the downsampling factor, and y of n be the output of the downsampler. X of n, this is y of n. So y of n can be represented as x of m into n. So taking the Z transform, y of Z is equal to summation n is equal to minus infinite to plus infinite x, sorry, y of n into z raised to minus n. Now this can be represented as summation n is equal to minus infinite to plus infinite x of mn z raised to minus n. Now Let us define a new signal. Let it be P of n, and P of n is equal to 1 for n is equal to 0 plus or minus d plus or minus 2d plus or minus 3d, like that. And P of n has taken the value 0 else. So we can write x of mn, that is the downsampled signal, can be represented as x of n multiplied with this P of n. So y of z can be represented as summation n is equal to minus infinity to plus infinity. Before that, x of mn z raised to minus n, and y of z, let mn is equal to u and n is equal to u by m. As n takes the value infinite, u takes the value infinite. As n takes the value minus infinite, u takes the value minus infinite. So my y of z can be represented as summation u is equal to minus infinite to plus infinite x of u into z raised to minus u by m. Now I am substituting the where x of u is actually x of u is actually x of mn. So it can be represented as P of n multiplied with the my x of n, that is P of u multiplied with the x of u. So y of z is equal to summation u is equal to minus infinite to plus infinite x of u into P of u z raised to minus u by m. Replacing P of u by its Fourier series representation as P of u is equal to, we have also P of u can be represented as 1 by m summation some variable k is equal to 0 to m minus 1 e raised to j 2 pi ku by m, which is the Fourier series representation of the P of u. So the y of z equal to summation u is equal to minus infinite to plus infinite x of u into 1 by m summation k is equal to 0 to m minus 1 e raised to j 2 pi uk by m z raised to minus u by m. Now let us take us minus n, usn for our convenience. Y of z is equal to summation n is equal to minus infinite to plus infinite x of n into 1 by m summation k equal to 0 to m minus 1 e raised to plus j 2 pi nk by capital M into z raised to minus n by m. On rearranging, I am taking 1 by m common outside and interchanging the summation m is equal k is equal summation k is equal to 0 to n minus 1 summation n is equal to minus infinite to plus infinite x of n into e raised to minus j 2 pi nk by m into z raised to, this is plus, minus n by m. So 1 by m summation k equal to 0 to m minus 1 summation n is equal to 0 minus infinite to plus infinite x of n into e raised to j 2 pi k by m z raised to, this is minus, I am taking minus 1 outside, 1 by m the whole raised to minus m. So this is equal to 1 by m summation k equal to 0 to m minus 1 x of e raised to j 2 pi k by m z raised to 1 by m. That is y of z equal to 1 by m summation k equal to 0 to m minus 1 x of e raised to minus j 2 pi k by m into z raised to 1 by m the whole raised to minus m. Let z equal to j omega. On substituting z equal to j omega, y of z can be represented as 1 by m summation k equal to 0 to m minus 1 x of e raised to minus j 2 pi k by m into e raised to minus, sorry, here there is no minus n, e raised to, sorry, this is e raised to j omega r, since z equal to r e raised to j omega, here I am taking rs 1 j omega by m. This is plus, that's equal to 1 by m summation k equal to 0 to m minus 1 x of e raised to j omega minus 2 pi k by, yeah. So this means that when I am taking the spectrum of the input signal to the downsampler, let it be this one, after the 0 to pi radians it will repeat, because CTFT will repeat after the 2 pi radians. And from this equation it is clear that there will be m minus 1 samples, m minus 1 spectrums in between these two. So there is a chance for overlapping the signal spectrum, and which seems to be an aliasing effect. So while doing a downsampler, there is a requirement of a filter or an anti-aliasing filter having the cutoff frequency fc is equal to less than pi by m, fc less than pi by m, followed by a downsampler. And this process, filtering plus the downsampler, is termed as the decimator. Thank you.